Ethernet technology has proven incredibly successful and is a near ubiquitous method of communication in the IT world. Up until now, the standard Ethernet system still cannot satisfy the real-time requirements due to the randomized media access and the best effort forwarding mechanism. However, in modern industrial automation, robust determinism and real-time performance are mandatory for process control and manufacturing systems. Therefore, the IEEE 802.1 task group is attempting to enable real-time and deterministic capabilities for Ethernet via a set of enhanced standards, namely time-sensitive networking. The primary benefits of TSN are to provide deterministic and real-time services, i.e., guarantee the bounded latency, low jitter, and zero congestion loss for various time-critical scenarios. As an IEEE-compliant, vendor-independent, and interoperable communication technology, it is the cornerstone for many industrial IoT applications in manufacturing. With these benefits, TSN plays a key role to implement Industry 4.0, and meanwhile facilitating the integration of information technology and operational technology for industrial IoT. Moreover, TSN is not only applied to the industrial domain, but is also predominant for other disciplines that require hard, real-time communication, such as aerospace, smart grids, and intelligent vehicles. In terms of different objectives, the published 13 TSN standards can be categorized into 4 groups, i.e., time synchronization, ultra-reliability, bounded latency, and resource management. Among these 13 standards, IEEE 802.1 QBV proposed the Time-Aware Shaper, which is the key component of TSN for guaranteeing deterministic and real-time transmission. The Time-Aware Shaper contains 8 priority queues, each with a timed gate that can be opened or closed. To schedule the traffic from different queues, Time-Aware Shaper is configured by an ordered list of gate operations, namely the Gate Control List. The Gate Control List specifies the gates of the priority queues that the Time-Aware Shaper should open or close to ensure transmission within specific time slots, thereby guaranteeing deterministic transmission. Therefore, a reliable scheduling algorithm is essential to compute the Gate Control List. We proposed a traffic scheduling method for TSN based on a non-optimization theory, i.e., bandwidth allocation scheme. Traffic scheduling method provides the user 3 key benefits. 1. Properly schedule traffic to satisfy firm, real-time requirements. 2. Schedule thousands of time-critical flow in milliseconds. 3. Achieve ultra-low latency by eliminating the queuing delays. We have implemented our traffic scheduling method into practice, namely uNest-CNC. uNest-CNC is a user-friendly, browser-based software used to create network topologies, compute schedules, and validate schedules through self-developed TSN simulation models. Our uNest-CNC can efficiently schedule a large-scale network with thousands of nodes and flows in a short time. The schedules computed by our traffic scheduling method can be configured to TSN-compliant devices from any vendor. Our uNest-CNC is suitable for any scenario that requires TSN to provide real-time transmissions, such as manufacturing, electric vehicles, and smart grids. In the following sections, we will demonstrate how to use our uNest-CNC and showcase its powerful performance. Our uNest-CNC can be conveniently accessed by using a web browser. Upon entering the website address, the user can view the comprehensive layout of the TSN scheduler. This tutorial provides an overview and subsequently elaborates on each detail. At the top, there are 5 pull-down tabs for different functions, namely Project, Topology, Scheduling, Simulation, and Video. In the middle area, users can create and modify the network scenario. uNest-CNC provides a device library at the bottom, allowing users to drag and drop devices to construct a topology. In the following sections, each feature of the uNest-CNC will be explained in detail, along with step-by-step instructions on how to create a network and execute the scheduler. The Project function enables users to save and load network configurations. It includes 3 subtabs: Open Project, Save Project, and Clear. Open Project allows users to load predefined network scenarios from their local PC. Save Project enables users to save the current network scenario to their local PC for future use. Clear also contains 3 subtabs: Clear Links, Clear Flows, and Clear All. Clear Links automatically removes interconnected links to create a different topology, while Clear Flows deletes all TSN flow configurations. Finally, Clear All deletes both links and flows. Topology allows users to edit or inspect the network configuration, which contains 3 subtabs, namely Discover TSN Network, TSN Node, and TSN Flows. Discover TSN Network allows the user to automatically discover the network topology from the running system. This feature is based on Link Layer Discovery Protocol, LLDP. Within TSN nodes, there are 3 subtabs, namely Summary, TSN Bridges, and TSN End Stations. The Summary tab displays the network configuration for both TSN bridges and end stations. Clicking on Summary opens a table that includes node name, type, model, port number, IP address, configurable, and related setting. Node name denotes the name of a TSN device. Type specifies whether the TSN device is a bridge or an end station. Model indicates the device model. Port number shows the available number of ports on the device. IP address denotes the IP address of the port. Configurable indicates whether the device supports TSN configuration through a value of true or false. Related setting is reserved for future use. TSN Bridges and TSN End Stations displays the configurations of TSN bridges and end stations respectively, and the specific content is consistent with that in Summary. When clicking on TSN Flows, a control panel for TSN Flows is displayed, which allows users to add, edit, or delete TSN flows. The flow specifications include a unique flow ID, flow name, source and destination, length in bytes, transmission period in nanoseconds, maximum allowable delay, and color. The flow ID is generated automatically by our uNest-CNC, while the other parameters can be defined by users. The Scheduling tab includes 2 subtabs: Compute Schedule and Show Gate Control Lists. By clicking on Compute Schedule, the uNest-CNC will be activated to calculate the TSN schedule based on the network topology and flow specifications entered by the user. When the user clicks on the Gate Control Lists of Bridge tab, the TSN schedule for switches is displayed in the form of a table, which includes switch name, interface name, hyperperiod, gate status, period, allocated flow, and period for columns. The columns switch name and interface name correspond to the TSN switch and its interface names, respectively. The TSN schedule is repeatedly executed at intervals of hyperperiod. The gate status column displays an 8-bit binary value, 1 for open and 0 for closed, indicating the status of the 8 priority queue gates. The period column represents the time interval for maintaining the current gate state, and the allocated flow column indicates the type of traffic that will be transmitted during the period. The period for column specifies the intended use of the period and includes 3 types of periods: best effort period for best effort traffic, GB period for the guard band, and the remaining periods are allocated for TSN flows. The gate control lists of talker displays the TSN schedule for a talker node, including node name, interface name, transmission time, the transmission period, and flow name. The node name and interface name represent the talker node and its interface. The flow name shows the name of flows generated by the talker node. The transmission time indicates the moment when the flow begins transmitting. The flow will be repeatedly transmitted at the interval of the transmission period. After calculating the schedules, users can validate them by clicking on Simulation, which uses self-developed simulation models. Upon completion of the simulation, the end-to-end delay simulation results are plotted in a figure. This allows users to quickly verify the validity of the schedules. Next, we will provide a step-by-step guide on how to use the software, covering 4 aspects: creating topology, editing traffic, executing the scheduler, and verifying the results with simulation. Firstly, we must create a network topology by selecting the Device button, dragging a device from the device panel, and dropping it wherever desired. The user can easily configure the parameters for an end station by double-clicking the device icon, which prompts a device configuration table to appear. The node name field specifies the device name, while model represents the device vendor. The configurable field indicates whether the device can be configured using netcomp yang. If checked, this signifies that the device is indeed configurable through this method. The IP address, port name, and MAC address can be set within their respective areas. Firstly, the TSN field signifies whether the current device supports TSN protocols. Users can employ a similar method to configure the TSN switch, with the sole distinction being an additional Spanning Tree Protocol Status field in the switch configuration page. This field signifies the spanning tree protocol status of the switch port, where disabled and blocking imply that the port is unavailable, and forwarding indicates that the port is capable of transmitting traffic. Next, we connect 2 devices by selecting them and specifying the interface, link length, and link speed. After repeating this process, the topology creation is complete. The next step is to add TSN traffic to the network. After completing the topology, we can add TSN flows by clicking the Topology button and selecting the TSN Flow tab. Clicking Add allows us to specify the flow name, source, talker, destination, listener, length in bytes, transmission period in nanoseconds, and its maximum allowable delay requirement. We can repeat this operation to add more TSN flows. It is worth noting that our scheduling algorithm has no restrictions on the number of nodes or flows, and our uNest-CNC can efficiently schedule thousands of flows within 1 second. After creating the topology and adding flows, you can initiate the scheduler by clicking the Scheduling button. The scheduler completes the computation in 590 microseconds. Remarkably, the scheduler is capable of scheduling thousands of TSN streams within just 1 second. Once scheduling is completed, you can check the scheduling results by selecting See Results to view the gate control list for the TSN switches. Alternatively, you can select Show Gate Control Lists under the Scheduling button to check the computed schedules for both TSN end stations and switches. The TSN schedules for switches consist of the gate status and the corresponding time interval required to maintain the specified status. On the other hand, for end stations, the TSN schedule only specifies the starting time instant for transmitting the TSN flows. Due to vendor-independent nature, The calculated TSN schedules can be easily configured to any TSN-compliant devices through standard configuration protocols, such as netconf. We provide self-developed TSN simulation models to validate the calculated scheduling results. By clicking on the Simulation button, the user can execute the simulation with the current network scenario and the calculated TSN schedules as inputs. Once the simulation is completed, the user can check the simulation results by selecting See Results. The result table displays the flow ID, delay constraint, and simulation end-to-end delay. Each row in the results table is interactive, enabling users to view the corresponding graph of the simulation results by clicking on it. The user can also switch to the previous or next numerical figure of the simulation results by clicking Pre or Next. The blue line represents the simulation results, whereas the maximum allowable delay is represented by the red line. As we can see from the simulation results, the blue line is well below the red line, and there is no network jitter. This indicates that the scheduling results are valid and can guarantee real-time transmission for a TSN flow.